So what they've given us is the angular acceleration alpha as a function of theta, where theta is given to us in revolutions. And it's during the first 30 revolutions. This goes from 10 radians per second squared up to a value of 20. Like that. Okay. I'll put my glasses on here. Okay. Now, let's draw a picture of the motion. Variable torque is applied to a rotating wheel at time 0. So here's the wheel, causing the angular acceleration to increase linearly with a clockwise angular displacement. So if we measure theta from here, clockwise angular displacement in this fashion. Hold it, did I read that right? Causes, clockwise angular acceleration. Clockwise angular acceleration.
It would be the same line that says clockwise angular displacement.
Okay, so let's just a second. So this is the positive sense of alpha. And that's what they gave us up here. And with a clockwise angular displacement of the wheel during that. Okay, so that's consistent. Theta, omega, and alpha all have that clockwise character for positive. During the, and increase linearly with a clockwise angular displacement during the next 30 revolutions. Okay, now this is 30 revolutions, so we need to multiply that by 2 pi per 1 revolution to convert this into radian measure. So we get 60 pi radians at that point. Okay, so we have that piece of information. Another thing that'd be useful, so this horizontal distance then is 60 pi radians, and the slope of this line then is going to be a rise of 10 radians per second squared divided by the 60 pi. So the slope that we see here on this function is going to be 1 over 6 pi, 10 over 60 pi. So the slope is going to be 1 over 6 pi. And this is theta now. This is our units of theta. Angular measure here. And so we have an equation then. Alpha can be described as a slope of 1 over 6 pi theta plus 10. So here's alpha as a function of theta. Alpha is a function of theta, linear function of theta. Now, what are we looking for? When the wheel has turned an additional 30 revolutions, so we're going to add plus 30 revolutions to the motion, its angular velocity is 90 radians per second. This yields an angular velocity of 90 radians per second. So the question is asking us to figure out the starting omega. So I think we have all the information we need now. All right, so how do we start?
Integrate that function. No, alpha equals dw over dt.
Do what? See,
No, you need the dw d theta or whatever the
omega.
omega, yeah.
Yeah, we're in Greek.
The,
Okay. Okay.
VdV equals ABS.
Okay.
The angular.
Yeah, very good. So think velocity. Omega d omega equals, think acceleration,
Alpha d theta.
think displacement. Okay. So the reason I wanted to do this is to get your brain into this mode. Okay. So then we can drop our alpha expression in there and integrate. So we're going to have omega d omega, and we're going to carry it from our unknown omega naught value, which we didn't know, and we're going to let this roll on up to 90 radians per second. And over on the right side, we have this linear function that we have to integrate 1 over 6 pi theta plus 10, integrated over theta from 0 to
Wouldn't it be the 60 pi?
Now, the one question I have, the reason I was reading the question so slowly was because what happens to this acceleration? Does this continue? Or after this, does this continue growing? Or does it just all of a sudden, that's the acceleration period, and now it's not accelerating anymore after it's covered that much?
I don't think that's an additional 30 revolution. It's asking. I think it's asking for what the conditions are, so as to have that angular velocity at the end of our acceleration window. So after 30 revolutions have passed.
I think that you just need
Do
to
you folks read the question that way as well? That's the issue I was pondering is well, two things. One, do we go an additional 30?
No, you only go 30 revolutions because
That's all they give you. You use
Okay.
what they give you.
yeah,
Good.
it's rotating at this angular
Good.
velocity, and then it goes 30 revolutions, and then it has this increased angular velocity of 90 radians per second.
Okay, so at this location.
Right, that's when
Yeah.
it's
So if I'd written this question, I would have phrased it a little more
different.
concisely in a way that we could understand that a little better. But I think through all of us, I think we got it figured out. So this is going to be associated, this omega is going to be associated with this location in the rotation. Okay? Now look at the right side integral right here. Alpha d theta.
That's an area.
What does that reflect up here on this?
Well, when you integrate it, it's represent the area.
It represents the area, does it not? And this is a simple trapezoid. Simple trapezoid. So that integral, we can carry out the math on it, which we'll do, but then we also could just double check ourselves by cranking out the geometric area of that trapezoid. So let's go ahead and do that. So what we end up getting over here is half of 90 squared minus half of our unknown initial starting angular velocity, half the square of that. And then over on the right side, we're going to get theta squared over 12 pi plus 10 theta. And our upper bound on integration on theta is going to be
60 pi.
60 pi, was the point we were pondering a few minutes ago. So we're going to evaluate this right side between 0 and 60 pi. Lower bound disappears. We get 3,600 pi squared on top, 12 pi on the denominator, plus 600 pi. And 12 goes into 36 three times, so we get 300 pi plus 600 pi is 900 pi. And we get 8,100 up here divided by 2 minus our half of our initial omega. If we clear the fractions out of that, well, I'll tell you what. $4,050. Let's just leave the 2 in there. We'll kick the omega naught term over to the other side, bring the 2 back over with the 900 pi, and so we're going to get negative of 4050 less 900 pi.
No, that's not right.
It's not, oh, if I kick that to the other side,
So it's going to be 4,050 minus that is equal to the 1/2
Yeah.
omega.
right, so we'll bring the 2 over and then square root this. I usually don't do all that kind of stuff like that quickly. I usually write the steps out, because who wins the race? The hare or the tortoise? The tortoise, okay. So I think that should pop out the correct answer. And our result, hold it. Okay, well, does that come out right?
Yeah.
Okay, good. And what did their answer turn out to be? 49.4, is that what you folks got?
Yep.
Okay. Approximately 49.4 radians per second. Okay, so what you want to do in some of these assigned problems is start to get your head wrapped around this rotational kind of concept, instead of thinking of things as translational kind of stuff, which is where we put a lot of our emphasis earlier. Questions? Pretty straightforward. Okay, let's look at the next topic then, which is absolute motion analysis.
What's the importance of having done this particular problem in radians? I mean, it's convenient to all have the same unit, but could we have converted the final answer into revolutions and just done the same thing?
Could have.
You need to be a little careful. Just all you have to do is just make sure that you're consistent in your units. So if you're going to leave this in radian measure, or excuse me, revolution measure over here on the omega side, then that means you're going to have to come back over here and treat your integration over theta in terms of portions of revolution. So now you can juggle things around like that, but you just have to be very careful about how you do it and make sure you don't develop some inconsistency in your work. Okay, there was a point that you were pondering yesterday, and let's come back over here for a second. You were pondering, could I take these omegas in the other direction or use my left hand on it? And you can certainly do that, and all you got to do is write out the vector algebra, and you can use your left hand if you, but you just have to come up with a proper consistency to be able to do that, and you can actually work it out and it'll come out right, but I caution you against that. I would suggest that you just kind of take it the way it's prescribed using our traditional right-hand system. Okay. So, absolute motion analysis. What you do here is you take your mechanism and you write a geometric relationship. So you write a geometric relationship that describes the type of thing going on. Now, where we have done this previously in the course is where we had constrained motion. We wrote, the way we were doing is we wrote a length of cable equation, right? And that was relatively simple to do most of the time. And then we differentiated that length equation of the cable to get our relationships that existed on velocity and acceleration. Now, what happens here in rigid body geometry is there are distances and there are that might be variable. Distances might be variable, but there's also angles that might be variable with time. So you write a geometric relationship that's going to involve not only lengths, but also angles. And then once you have that geometric relationship, you then differentiate. Okay? Now, it's a very nice approach if the geometry is not too complex. If the geometry is too complex, then you may not ever see it. You may not ever see what that geometric relationship is. And then what you have to do is you have to fall back on your vector algebra skills. And it's going to be a relative velocity and relative acceleration kinds of equations that you'll write, which are pretty easy to write, and then you just crank out the vector algebra or calculus. So the key on using this approach is to come up with a geometric relationship, then differentiate. If that fails, if it fails, then you're going to have to rely on relative velocity and acceleration analysis, which we'll be getting to next week. So, I'm going to give you a handout next class session, but I want to go through a classic problem in absolute motion analysis. The rolling wheel. The rolling wheel. So if this is the center of our wheel, and let's give this thing some omega, and it might even have some alpha associated with it. Let's put a spoke on the wheel. What's this point doing down here as this wheel rolls?
Just sitting there for an instant.
Okay. How'd you know that? Just because you've been riding bicycles and...
Well, that and the wheel isn't slipping at all as it goes.
Right. Okay, everybody good with that? Okay. That point is instantaneously at rest. Now, when we introduced the concept of fixed axis rotation yesterday, then, and this is a rigid body, then momentarily this point's at rest and this mechanism or this rigid body is rotating about that point. So, how fast is the center moving? If this is the fixed point, and remember yesterday I etched lines on a blob, okay, and that thing could be in motion then, and it might be in translation and in rotation at the same time. Well, right now we've actually got a pretty simple case. You can think of that as temporarily or momentarily a fixed pivot point. So how fast does this point have to be moving, and in what direction? It has to be moving at r omega, doesn't it? Which direction? To the right. Feel good? Oops. All right, okay. How fast is this point up here moving? Yeah, this is the momentary fixed axis of rotation. That point's got to be moving at twice that. As a matter of fact, you can look at a profile along this line and see that that point's got to be moving scaled up, because the only thing variable changing on that is the lever arm. When I came to Oregon 30 plus years ago, the first week I was here, I used to ride my bike a lot, still do fairly frequently. But the first thing I did moving here after being in California is I put fenders on my bicycle the very first week. Why? How come? Because I didn't like having that stripe all the way up my back, okay? Okay. So how do you get your back wet when you're riding your bike zipping down the road? Here's the rolling wheel, huh? It's coming. I'll tell you what, using the same thought we just had, well, right now, I think you see that we've got the top of that wheel moving twice as fast as the center of the wheel, as the bike going down the road. Now the water, a lot of the water doesn't get up onto the top of the wheel. What happens? Because of the dynamic motion,
The wheels accelerated out on the bottom.
yeah, there's a normal acceleration, and so there's a tendency for particles to leave in a straight line. And if there's not enough surface tension between the surface of the tread of the tire and the water, that particle of water is going to leave the surface of the wheel and then be a projectile. So as I used to get wet on my backside riding my bike, I'd think about that, you know, knowing a little bit about dynamics. So how fast is this point moving over here? It's pivoting around this, isn't it? Isn't it pivoting around this? And what direction is this point moving? Is it moving straight up?
It's moving at an angle.
It's moving kind of an upward angle.
Isn't it moving perpendicular to this line? What angle?
45 degrees from horizontal.
Yeah. And this is your radius right here, isn't it? And isn't this square root of 2r? That length? So how fast is that moving?
One and a half times faster than the motion of the...
It's square root of 2r omega. That's 140% of the speed of the bicycle. How about a point a little further up? How's it moving? Perpendicular to that. Aiming towards 200% of the speed of the bicycle. So a lot of the water that's on the surface of that tire, because of the break in the surface tension that occurs, it's going to become a projectile somewhere up in here as this thing accelerates, as this water is particles that picked up off the floor down here, picked up off the surface of the ground, and put onto the tread of the tire, and then as that wheel moves forward, that velocity is speeding up from 0 to 200% of the forward motion of the bicycle. Pretty cool. And then besides that, you have a little vortex behind you of air, right? And so that probably even accentuates it even more. So you wear rain gear and you have fenders on your bicycle, and then you're okay. All right. You got the idea? Fixed axis rotation? Isn't that pretty slick? Okay. So now I need to redraw this because I was having so much fun talking about the water and the wheel that I didn't come up with this geometric relationship. I didn't come up with this geometric relationship so that we can actually look at the mathematical analysis. So I'm going to redraw it. Can I erase this?